From space, Earth shimmers like a blue marble. This is our home, a planet defined by its vast oceans. But why are the oceans blue? Well, sunlight bathes our planet in a rainbow of colors. Water molecules dance with light, absorbing reds and oranges, while reflecting blues and greens. This scattered blue light is what reaches our eyes, painting the oceans in hues of azure and indigo. Yet this familiar blue wasn't always so. If we journey back billions of years, we'd find a very different Earth, with oceans not of blue but of green. Imagine a young Earth, its surface still forming, volcanoes erupt, spewing gases and molten rock. The atmosphere is this hazy mix, totally lacking the oxygen we breathe today. In these primordial seas, life began. Simple organisms thrived in a world without oxygen. These early life forms colored the oceans in shades of green, a testament to their unique chemistry. So how do we know about these green oceans? The clues lie hidden in the Earth itself, locked away in ancient rock formations. Scattered across the globe are banded iron formations, ancient geological structures that stretch across continents, from the rugged outcrops of South Africa to the vast, rust-colored landscapes of Western Australia. These formations are geological wonders, striped with alternating layers of red and dark minerals, iron oxides that shimmer under sunlight, each band a silent witness to a world long gone. Acting like time capsules, these rocks preserve the chemical fingerprints of Earth's early oceans, offering scientists a rare glimpse into the planet's formative years, over 2.5 billion years ago. Back then, Earth's oceans were vastly different. They teemed not with life, but with dissolved iron, leached from volcanic rocks and spewed from hydrothermal vents deep beneath the sea. The atmosphere lacked free oxygen, and the seas were murky, rich in minerals but inhospitable to most modern life forms. As primitive photosynthetic organisms began to emerge, they released small amounts of oxygen into the water. This oxygen reacted with the dissolved iron, forming insoluble iron oxides that slowly sank to the ocean floor. Over millions of years, this process repeated layer upon layer, creating the striking banded patterns we see in these rocks today. Each layer a chapter in Earth's evolving story. These bands are more than just mineral deposits. They are records of the Great Oxidation Event, a turning point when life began to reshape the planet's atmosphere and oceans. The formations stand as monuments to this transformation, their iron-rich layers capturing the moment when oxygen began its slow rise, forever altering the course of life on Earth. In those early days, the oceans were painted in hues of green and brown, colored by iron and other minerals, a stark contrast to the blue waters we know today. Today, these ancient rocks whisper stories from a distant past, reminding us of a time when the Earth was young, and life was just beginning to leave its mark. The story of Earth's oceans is intricately linked to the evolution of life. Enter photosynthesis, a revolutionary process that would reshape our planet. Early life forms like cyanobacteria developed the ability to harness sunlight's energy. They absorbed sunlight, using it to convert carbon dioxide and water into sugars, releasing oxygen as a byproduct. This oxygen, toxic to many early life forms, began to accumulate in the oceans and atmosphere. The stage was set for a dramatic transformation, a shift from green to blue. In the distant past, Earth's oceans were vastly different from the deep blue expanses we know today. They were rich in dissolved iron and tinted green, a reflection of their unique chemical makeup. But everything began to change when oxygen started to accumulate in the atmosphere and oceans, thanks to the emergence of photosynthetic microorganisms like cyanobacteria. As oxygen levels rose, the dissolved iron in the oceans began to react in a dramatic and transformative way. Oxygen molecules combined with iron ions floating in the seawater, triggering a chemical reaction that formed solid iron oxides. These oxides, essentially rust particles, were no longer soluble and began to precipitate out of the water. Over time, they sank to the ocean floor, forming thick layers of iron-rich sediment. These ancient deposits are now known as banded iron formations, and they serve as geological evidence of this monumental shift in Earth's chemistry. This process, known as oxidation, gradually stripped the oceans of their green hue. As the iron was removed, the water became clearer and less murky. The reddish-brown tint from the oxidized iron gave way to a more transparent ocean, allowing light to penetrate deeper and setting the stage for new forms of life to thrive. With less iron to absorb red wavelengths of light, the oceans began to reflect the blue of the sky more vividly. The transformation from green to blue was not just a visual change, it marked a fundamental shift in the planet's environment. The rise of oxygen was a turning point in Earth's history. It enabled the evolution of complex oxygen-breathing organisms from simple marine life to the vast diversity of animals we see today, including us. This oxygenation event, often called the Great Oxidation Event, was both a crisis and an opportunity, wiping out many anaerobic species while opening the door for new life forms to emerge and flourish. But the story of green oceans doesn't end there. Even today, certain regions of the ocean can appear green due to the presence of phytoplankton, algae, and varying mineral content. These modern green hues are a reminder of our planet's dynamic past, and a testament to the ever-changing nature of life on Earth. Off the coast of Iwo Jima, Japan, volcanic vents release a plume of iron-rich water into the ocean. This iron, exposed to oxygen, forms a distinctive green plume, kind of like a miniature echo of ancient oceans. This modern-day example shows that green water rich in iron can actually support life. In fact, these green waters teem with microscopic algae, showcasing life's remarkable ability to thrive in diverse environments. Cyanobacteria, also known as blue-green algae, are true masters of adaptation. These ancient organisms possess pigments that allow them to thrive in environments with varying light conditions. In addition to chlorophyll, which absorbs red and blue light, they contain phycoerythrobilin, a pigment that captures green light. This allows them to flourish in waters where green light penetrates most deeply. This adaptation to green light suggests that early cyanobacteria were well suited for life in iron-rich green oceans. Their ability to thrive in these conditions played a crucial role in shaping Earth's atmosphere. The transition from green to blue oceans was a gradual process, unfolding over millions of years. As oxygen levels rose, the oceans slowly cleared, revealing the blue depths we know today. This transformation wasn't just about color. It reflected a fundamental shift in Earth's chemistry and the life it supports. The rise of oxygen allowed for the evolution of more complex life, eventually leading to the incredible diversity we see today. The oceans, once a canvas of green, transformed into the azure expanse we recognize now, a powerful testament to the ability of life to shape our planet. The color of our oceans is not static, it is a living, breathing reflection of the planet's health. From the deep navy blues of the open sea to the vibrant turquoise of shallow reefs, these hues tell a story, one written by sunlight, microscopic life, and the chemistry of water itself. The ocean's color reflects the delicate balance of life and chemistry. Phytoplankton, the tiny organisms that form the base of the marine food web, play a major role in this. They absorb sunlight and carbon dioxide, and in doing so, they influence the color of the water. Where they thrive, the ocean may appear greener. Where they are scarce, it may look bluer. And as our planet continues to change, through rising temperatures, shifting weather patterns, and melting ice caps, so too might the color of our seas. These changes are not just aesthetic, they are signals, warning signs of deeper transformations occurring beneath the surface. Pollution, climate change, and the relentless expansion of human activity are putting immense pressure on marine ecosystems. From plastic waste choking marine life to carbon emissions altering the ocean's pH, our actions are leaving a visible mark. Coral reefs are bleaching, fish populations are declining, and once clear waters are turning murky. These are not isolated events. They are part of a global pattern of disruption. These changes could manifest as shifts in ocean color, offering a visual cue to the health of marine environments. A greener ocean might indicate an overgrowth of algae, while a duller hue could signal a loss of biodiversity. Satellite imagery now allows scientists to monitor these color changes from space, providing real-time data on ocean health. Algae blooms, for instance, can be tracked as they spread, sometimes naturally but increasingly due to nutrient pollution from agriculture and urban runoff. By studying the oceans, both their past and present, we gain a deeper understanding of the interconnectedness of life and our planet. Oceanographers, marine biologists, and climate scientists are working together to decode the messages hidden in the waves, but it's not just up to scientists. Each of us has a role to play. From reducing plastic use to supporting conservation efforts, our choices can help restore balance to the seas. As we look to the future, Let us strive to protect these precious waters, not just for their beauty, but for the life they sustain. The oceans are a source of wonder, mystery, and life itself. Let's ensure they continue to inspire awe for generations to come.